It's okay. Hello and welcome to Calculus 3. So what's Calculus 3 all about? Well, it's Calculus 1 in 3D technically. No sequences and series in this course, I'm sorry to disappoint you, but we'll deal with the rest. That is going to be limits, derivatives, and integration. So Calculus 3 is technically Calculus 1 on steroids. It's a three-dimensional calculus, and you will find that for most of the course you will be doing Calc 1 problems 3 times. This class will have a lot of formulas and things, and actually that is what Calculus 3 is. We are not learning new ways of integrating or taking derivatives, so everything that you know from your Calc 1 and Calc 2 class will be used in this class. We are not learning any new methods of integration. However, when I put 3 functions into a vector and I call that vector valued function, and you have to find the limit or differentiate or integrate, you are technically doing 3 Calculus 1 problems independently. So you need to be masters of Calc 1 to survive Calc 3. Calc 2 will offer you few integration techniques, but the most important part, obviously, from Calc 2 that you need for this class is Chapter 10, which is parametrization and polar coordinates. We are going to see once or twice maybe integration by parts, and we'll stay away from trig integration and trig substitution and all of these things, because we have powerful tools in this course to transform our integrals from one realm to another and bypass those heavier integrations. So what you absolutely must know to survive this class is U sub. I mean, if you don't know that, then, I mean, how did you make it here, right? U sub is technically half of your Calc 2 class. So what are the things that you absolutely must know? Well, first off, obviously, limits, derivatives, and integration. Limits contain the basic limits and then L'Hopital's rule, because we are going to see some of those show up. Differentiation, and whenever you say differentiation, you mean 95% you mean chain rule, right? That's technically what it is. And then when you're talking integrals, again, 95% U sub, and then the rest is split between by parts and basic integrals. You need to know how to solve definite integrals, right? Ones with limits, and so on. And then that leads into the stuff. So let's go in order. So when you have limit of, let's say, x goes to infinity of e to the x divided by x to 100, we would use the concept of, well, you say, okay, let me just plug in, oh, this is infinity over infinity. So what I can do is I can do L'Hopital's rule. Yeah, sure, but you have to do L'Hopital's rule 100 times. All right? So growth rate of functions will help. So you can go and do L'Hopital's rule 100 times and eventually end up with e to the x over 0. Or you can just say, well, wait, can't I just, oh, sorry, not over 0, over whatever, 100 factorial. Or you can just say, well, wait, growth rate of functions, e to the x grows faster than x to the any power p. Therefore, the limit x goes to infinity is of e to the x over x to 100 is equal to infinity. Did you make it? Nice. So that's that. Or if you flip this and you have the slower rising function in the numerator, it collapses to 0. So growth rate. Growth rate helps when solving limits to this. Now, if you have some basic limits, like limit x goes to 3 of x squared minus 2, well, then there's just 7, right? Because nothing special happens there. If you have the limit of, let's say, sine x over x as x goes to 0 and you haven't memorized the solution, you can use L'Hopital's rule, because this is 0 over 0, and we know that's indeterminate form, so we'll get cosine x over 1, and as you plug in 0 now, you get 1 over 1, which is 1, and that is your answer for that using L'Hopital's rule. So these are the main ways of taking limits, using the growth rate if the limit goes to infinity, plugging in if nothing weird is happening, i.e. no 0 in denominator, and then also using L'Hopital's rule. Now, L'Hopital's rule could be used on the top 2 examples, obviously. You just have to do it 100 times, and it's not fun. So that's the story of limits. Derivatives. For derivatives, we are mainly looking into the chain rule. So chain rule is the most important and the most frequent derivative taking technique, and you guys need to be able to do that even in your sleep. There will be a lot of derivatives, and we are going to learn partial derivatives in this class, and the chain rule for Calc3 is going to look different than the chain rule that you know and love from Calc1. It's going to be much more complicated. And actually, you will have to develop the formula every time you want to take the chain rule, because the formula you use to take the chain rule, right, to take the derivative, is going to depend on the features that your function has. So there is no one formula for chain rule to learn in Calc3. There's actually infinitely many. So we learn how to draw a tree and then develop the formula from that tree and then use the formula to take the derivative. So it's a little bit more convoluted, but very possible. So you guys will have a little bit different rules for chain rule when we get there eventually in chapter 12. But even prior we get to chapter 12, we'll be taking derivatives in chapter 11 as well, and we need to know how to take derivatives. So the derivative of cosine of 3x is sine of 3x divided by 3. The derivative of e to the x squared by chain rule is e to the x squared times 2x as a chain. The derivative of 3 over x squared plus 1 is not the quotient rule, because that's going to waste your time. You are going to rewrite this as a chain rule, kicking the 3 in front of the integral because it's constant. What happened? Oh, that was a sneeze? Nice. Good effort. X squared plus 1, and then we put the exponent of negative 1, and then we have negative 3 x squared plus 1 to the negative 2 times 2x as a chain rule, which gives us negative 6x divided by x squared plus 1, everything squared. So these are some basics of limits and derivatives that we are going to see as we go through the course. The one that most concerns me is integration. And the reason is, so far you only had one-dimensional input in your integrals, and since it was one-dimensional input, you never had to worry about dx. And I'm highly allergic to people that do not worry about dx. I'll explain why as we go through the course. Dx, dy, dz, dy, dz, dx, or dy, dx, dz, or whatever order you put them in, it's going to matter a lot. And the story of dimensions and a 3D coordinate system and going all the way into the fourth dimension because you have a 3D object that is going to have a fourth dimension represent density, which could be variable density. It could represent the temperature distribution within the object, because you know that if I heat on one end and the most of the heat is concentrated there and not so much on the other part, so there is a function on which that heat propagates through the object. So if I have a third-dimensional function representing the shape of the object, whatever it is, well, what's the fourth dimension? Fourth dimension could be either the temperature, or it could be density, or it could be whatever other attribute you have that is happening within that particular object. So yes, this is going to go all the way into fourth dimension, and we are going to see that within the triple integral. You will have a triple integral to describe the boundaries and the shape of the object, and then whatever function you place into the integral will be that fourth dimension thing, and then together you will be integrating and doing stuff. Now, it's extremely important to understand the dx business so that you are able eventually to set up integrals and operate in Calculus 3. So we start from the beginning. The Riemann definition, right, using the sum and limits and all of that kind of stuff, is built by understanding that we can approximate the area under the curve if we calculate area of each individual rectangle that we have over here and add those areas together. Now that creates this error, and as you can see, there is a lot of error on this. So green over here, that's error. So now we know that the width of each one of these rectangles is delta x, and we know that the height is when you compute your xi, I being a counter, not imaginary number, by a counter like x1, x2, x3, x4, so it's just a location on x-axis. If you calculate x function at xi, you will calculate the height of the rectangle, and you have your delta x. When you multiply a times b to find the area of the rectangle, I can find the area of the rectangle by multiplying my f of xi times delta x. So this gives me the area of one rectangle. But I have many of them. So what I'm going to do is I'm going to add, I goes from 1 to n, and I'm going to say add many rectangles. And I know that more rectangles I have, the better the precision, the less error, right? So if I send eventually the number of those rectangles to infinity, now I'm adding infinitely many rectangles, and that is going to be exact area. Therefore, I am getting the integral a to b of f of x dx, and there's your calculus 1. Now, do you see this? Yeah, you should know from calculus 1 differentials that dx is the same as delta x, and delta x is defined as b minus a over n, number of rectangles. So that dx is not there as a notational decoration, right? Oh, I need to put something at the end, right? It's cool. No, that is actually a dimension to multiply with. That is the width of your rectangle. If you are calculating the area of the rectangle, which is this, as height of the rectangle times the length of the rectangle, your delta x is the length of that rectangle. You can't compute the area if that is not there. So it's not there for decoration. It must be there. It's not just notation. It is actually a dimension that you are multiplying. So when you are examining the dimensionality of the formulas, you start by saying area is the integral from a to b of f of x times dx. And you know what I have? Over here in blue, I have the height, and over here I have the width. Now, we know that this dx is the width because dx is the same as delta x, and delta x is b minus a over n. And here is the connection between this a and a b and a dx. They're a group. They work, right? And this squiggly line for the integral is s. That stands for sum. So this formula here is the shorthand notation for the long formula that I have over there, up there with the limit and sum and all that kind of stuff. The squiggly line is stretched s, right? It means hope on kryptonite. So you have s, which stands for sum, and that's what adds all of the infinite amount of rectangles that are under the function between a and b. Now that dx is the one that actually has a and b divided by n, and that n goes to infinity. So when you go from 3 to 5, this is 2. 2 divided by infinity is infinitely small. So how wide is each one of your rectangles? It's infinitely thin. It's pretty much 0 in thickness, so it fits under each single point under the function. There are infinitely many points between any two numbers. Infinitely many points between any two numbers. So therefore, you have infinitely thin rectangle under each point of the function. There is no room for error, and that's why the area is exact. So now, if you want to compute the area under the curve for x squared, from 1 to 2, you will simply write area 1 to 2 of x squared dx, which is x cubed over 3 from 1 to 2, which is 8/3 minus 1/3, and gets you 7/3, I hope, or whatever. It's just numbers. So we have a way to compute area under the curve. So now what I want to do is I want to take a look at the triangle. Now this triangle has 1, 2, 3, 4, 5, 6, 7, and 4. There we go. So 7 and 4. We can calculate the area of this triangle by using 1/2 base times the height, and in our case that's going to be 1/2 7 times 4, which is clearly 14. So area of this triangle is 14. Now let me paint you a picture. You're tutoring a middle school kid, right? Because that's where you make your money, right? And area of the triangle came up. You said, well, the formula is 1/2 b times height, right? And you work it out, and the kid goes, why? Oh, let me show you why. Right? And you obviously use integrals, right, to explain, because that's what we do. So what do? You say, I'll take a representative rectangle over here, delta x, right? And then that delta x clearly slides from 0 to 7. Having this as its function, oh, that's a linear line, right? We know the function for that linear line because we have that this location is 4 and this location is 7. It's a line that falls to the right, so the slope is negative on it. Rise over run, that's 4 over 7, so negative 4 over 7x plus 4 dx. And that's why. It's obvious. So this calculation better give us 14, or we close the book on calculus and don't have to worry about it. Right? So we have negative 4 over 7 times x squared over 2 plus 4x computed from 0 to 7. That's our calculation. These two die, so I have negative 2/7 times 49 plus 28, and then I have minus plus 2 over 7 times 0, and then minus another 0. No one cares about that. So these guys cancel, and I get negative 14 plus 28, and there is 14. That's why, you say to the kid, right? It's obvious, right? If there is a second y, well, you can do the integral as delta y integral, because that's okay as well, right? If you set up the same integral, so the same area we did before, now in green this time, you are going to see 0 to 4. Oh, whew. Now we have to, right, this is going to be dy integral, so we need to change our function in terms of y. Right? You can't have the integral being y limits and dy and have function in terms of x. Right? That's not defined yet. So if your limits are y1 and y2 and your integral is in terms of y, then your function that goes in here better be in terms of y. Now you already have that y is equal to negative 4 over 7x plus 4. So just massage that little bit and you will have it as x equals everything else, right? So you have y minus 4 is equal to negative 4 over 7x, and from there x is equal to negative 7 over 4 y minus 4. Great. That goes here. Negative 7 over 4 y minus 4. Guess what the answer for this integral is? Exactly. See, I put these 3 dots, and then I put 14, and then I just put that. What is that? Just do it, exactly. Because you will eventually go home and you might look at this and be bored, right? So you have something to do. So there will be some of that stuff along class. So whenever I put this symbol, that means when you are reviewing this stuff at home, just, you know, do a quick calculation to make sure that you have this stuff, right? Also contributes to your carpal tunnel in some cases, you'll see. Or developing one if you don't have it already. I mean, you're all gamers, right? What? I had like 2 people shake their head, yes? I'm leaving.
I wear a splint on my wrist overnight, if that helps.
Good. Now, why was this example, it was triangle, who cares, right? We can use just a basic formula. Did anyone pick up what I actually wanted to say with this example? Like what I was trying to put forth? Why do you do this? Yes?
Maybe to have the importance of delta x.
Yes! That's it. The only reason why I did this example is to talk about delta x and delta y. Right? Hopefully you can do the calculation of the integral. Hopefully you can integrate, right? So Calc 1. What was never stressed before enough, and now it's crucial to your survival in chapter 13, is ability to understand that all of the delta x's line up one by one vertically perpendicular to x-axis, and you take the first one, which is the lower limit, and the last one, which is the upper limit, and when you have the dx, you have to understand that setting up the integral dx is going to be x1, x2 function in terms of x dx. If you switch to dy, it's going to be y1, y2 function in terms of y dy. What you absolutely must know is entire integral has to be x, 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 or y, y, y. And then order in which it goes. Because soon enough, see. Do we have anything over here? I didn't want to do this. Boom. There we go. Chapter 13, right? Now this is going to be extremely easy when you get there. Only if you understand the layers of the onion, right? Which way the dx belongs to the limits. So, the dx over here belongs to the limits over here. And the dy over there belongs to these guys, and then these guys here with this arrow, I don't know how to put these guys, there we go. Right? So the way to solve these triple integrals is you do this one first. This is like the inner part of the onion. You do that first. You ignore what's on the ends. And then you do the next one. And then the end. It's actually 3 Calculus 1 problems. It just looks bad. It's incredibly easy if you understand. Now, what's hard? What's hard is to take a look at the picture up there and then come up with this. This is your job as engineer. Do we have mechanical engineers? There you go, that's your life right there. No one cares if you can integrate. We have computers. See, computers can't set up integrals yet, right? But if you need to figure out the volume of this shape here, this is rounded here. It's like a skateboard or a bicycle ramp or a snowboarding ramp, whatever you want to call it, right? It's a ramp. You can come in from this end, like, and launch yourself up. It's curved. What's the volume of that, right? So for the volume of that, we don't need the 4th dimension here, so we kill this thing, right? Now you have a triple integral with 3 dimensions. 1, 2, 3 dimensions, right? And this is why I'm saying that this dx, dy, dz, that's not a decoration, guys. You have to understand that these things will play a role, a big role, in setting up the integral. You see the extra picture that I have, and look, I draw dx over here, right? Now, those of you that are vicious, you might find this from the last semester right online and go and look up what happened there for that problem. But it's coming up in chapter 13, so we are not in a rush to cover and learn this today. What I'm trying to say now is what you must know, that is a Calculus 1 realm, the dx belongs to the x limits. And if you look at my x-axis, 0 to 1, see? That's that line, 0 to 1. That's where my object is. It's between, on x-axis, is from 0 to 1. And that's what I have, right? So setting up these integrals, it is going to be actually looking into dx, dy, dz at all times. And we are going to upgrade these dx, dy, dz's, which are two-dimensional now, right? Because if I draw dx is just a two-dimensional rectangle, very thin. We're going to upgrade that into from representative rectangle into representative French fry, and representative pizza slice, and other things that will come up. So we'll deal with that. So back to our class. The next part is the talk about chapter 10. Here we meet parametric equations and polar coordinates. So what parametric equations do is they split dimensions. Now, what does that mean? Well, think about it. If you have a function, let's say y equal x squared, you have a dimension x and you have dimension y. So what I'm going to do is I'm going to take this function and I'm going to express these dimensions in terms of a common parameter. So for 2D problem, I'm going to have a set of two parametric equations. Now you're going to say, well, you just made it worse, because earlier you just had a parabola. Now you have a linear function and a parabola, and it's not that much different. Yeah, it's not designed for these new problems, right? It's designed for more complicated stuff. So this is what we would call trivial parametrization because of this, right? So technically your second equation is guaranteed to be the same as the original equation. You can do this trivial parametrization on any function or non-function that exists, right? And you achieve actually nothing. Where this stuff is powerful is when you reach the functions which, when you reach equations which are not functions. For instance, circle, radius 3. Has equation x squared plus y squared equals 9. Can you differentiate this? Yeah, use implicit differentiation, right? Who remembers implicit differentiation? Yeah, that's what I taught, 6 of you. Right? But with a little bit of magic, I can rewrite this as x equals 3 cosine t and y equals 3 sine t. Ooh. Both of these are functions. And what can I do with functions? Everything, right? I can do everything with functions. So you see, the parametric set can take something that it's not a function, break its dimensions. Each dimension gets its own equation, and each one of those equations is a function. And that is the huge advantage. Now we don't need implicit differentiation anymore, because what we have are functions, and we can deal with that, right? So parametrization is very powerful. Now, another part is orientation. You see, in parametrization, we are introducing a parameter t or parameter theta or s, whatever, and that grants us another degree of freedom. If you introduce t and you want to call it time, you can track progression of a line in time, which gives it orientation. Which way do you draw the line? Is it clockwise or counterclockwise? This will be crucial in chapter 14. We'll be dealing with parametric equations in chapter 12, but orientation is coming into a play in chapter 14. So for orientation, I have x equals 3 cosine t and y equals 3 sine t to give me a circle of radius 3. And also x equals 3 sine t and y equals 3 cosine t to give me the same circle with radius 3. What's the difference? The difference is orientation. The upper one has orientation counterclockwise, and the one on the bottom has the clockwise orientation. This is simply tracing in time which way the function develops as you compute these guys. You will compute these the same way you did in the middle school. You are going to assign values for t, let's say 0, pi over 4, and pi over 2. And then you will calculate x and you will calculate y. I don't care which one you do. Now, if you pick the top one, you will start at 3 over here, and you will go counterclockwise. So you will have t equals 0, t equals pi over 4, and t equals pi over 2. And you can see that, right, that the time progresses, right, because time of pi over 2 is about 1.5 seconds, let's say. So you go from 0 seconds to 0.7 seconds to 1.5 seconds. So clearly, as time progresses, the point at 3 goes around the circle, tracing the circle counterclockwise. But if you look at the bottom part and start at t equals to 0, t equals to 0 now gives you 0, 0, 3. So this is your t equals 0 now. Right there. Because when you plug in 0 for sine, you get x is 0 and y is 3, because cosine of 0 is 1. And then when you plug in the next point, you will get this one, and the last one, t equals pi over 2, will actually be there. So now you see that the progression in time is clockwise. What is different on this parametric set? I swap sine and cosine. So they both graph the circle, but the orientation of that circle is flipped. Which way do you draw the circle, right? That way or this way? Again, it will come up in chapter 14. We can chill about it now, but I just need to make sure that for the sake of completeness of all of this first introductory lesson, that that's there. So we're done with parametrization. And let's do one more. No, we can't do that one. We can do this one. All right. So more parametrization. So you know the basic parametrization, right? The dummy one, when you do this. So technically, if you're starting with a function and you need parametric equations, well, that's your go-to method, right? You take x equals to t, and then you just substitute x's with t's, and you're done. Ellipse is another cool one. It has two different radii, major and minor. So parametrization for something like this would be A cosine t and y be sine t for the orientation in a counterclockwise direction. This is yet another way to see that the through parametric equations, that the circle is just a special case of ellipse, just like square is a special case of a rectangle. Square is a rectangle with all sides the same. Circle is an ellipse with a equals b, which equals r, right? So that's all it is, if you haven't made that connection before. So now you see that if you make A and B the same, you get the circle. If you keep them separate, then, you keep them different, you get an ellipse. And that's that. Polar coordinates. So this is your 10.2 and 10.3 crash course, right, from Calc 2. And what's happening with polar coordinates? Polar coordinates are developed to supplement your regular XY rectangular realm. You are used to XY coordinate system. You have one on the ceiling. That's the XY coordinate system. We can trace the location of every student by using that as a grid, right? And we can assign 0, 0 in one of the corners of the room, or whatever that plastic thing is, and a router or whatever it is. That could be 0, 0, and then pick y-axis, pick x-axis, and then just look up and you see, oh, okay, there's the intersection over here. So you can count, right, how many squares you have. That's just a standard grid. You can impose those kind of grids on surfaces, and then you can design objects. One of the cool things. So here is I don't know if I have it. Give me a second. Yes, I do. Nice. Now, does it have battery? Yes. You can have fun, right? So that's a keyboard, actually. It's Bluetooth functional keyboard. You connect it to your cell phone and you can use it on any surface. How does it work? Same thing. It's a grid. It's the XY grid. It picks up so the laser picks up the location of your finger, right? It works on any surface. So the idea is that you can take the surface and you can partition it as a grid, and you can find any location on that surface by having the x and y coordinates. GPS works the same way, right? Because all you do is from the satellite that will oversee a certain area, well, 3 satellites, but fine, just makes that surface flat, right? And then you have the x and y coordinate system, and then you can find your directions. So all of that stuff works. Now, what are the polar coordinates then? Why do we need this stuff? Well, the XY realm doesn't work well with curves. So if I need to locate a point, I can go 3 units this way, and then I go 2 units up, and then I know that the location is 3, 2. Awesome, right? But then we run into issue that if I have a circle with a radius 3, I get the equation that it's not a function, and then I have to suffer through parametrization, or integration of a circle is amazing, right? You have to use trig sub, right? in order to find the area of this, let's say you don't know the area of the circle, or you just did that tutoring and you said, oh yeah, area of the circle, pi r squared, and the kid goes, why? Well, obviously you're going to set up the integral, right? But setting up the integral, then you have to use integral, right? You want dx integral. Let's set it up. So that's going to go from 0 to 3. And since it's only calculating 1/4 of the whole thing, you have to go 4 times the integral. Now you have 9 minus x squared dx. Remember, the function has to be in terms of x, right? And that is a trig sub integral from Calc2, right? Good luck. Now, what do polar coordinates do? They make a joke out of this. Because the polar coordinates say, well, in our conversion, x squared plus y squared is actually r squared. So your equation that you had before, x squared plus y squared equals 9, becomes r squared equals 9, from where r is equal to 3. So your really nasty equation in Cartesian rectangular coordinates became just r equals to 3. What's easier than to integrate a constant? Right? So you see that the polar coordinates take certain integrals and things from our rectangular world that require work and sweat, especially in this temperature that we have here now, and turn that into a joke. So these two systems are not really competing, you know? They complement each other. They really, you're designed that the world of rectangular coordinates is going to deal with these objects that are sharp and straight, and you know, the rectangles and triangles and all these kind of things. As soon as you start getting into the curves, switch to polar realm. So what is the polar realm? Well, the point in it is r theta. And the way it works is, it's still on xy coordinate system, but it works differently. You first stretch radius if you want to graph r theta equal to, let's say, 3 and then pi over 4. So the way you do it is you stretch the radius to 3 first, and then you swing that to the pi over 4 area. And that's your 3 pi over 4. It's going to be some ugly decimals for that point in rectangular, but that's okay. The rule is, what's ugly in polar coordinates is beautiful in rectangular coordinates, and vice versa. Okay, that's the rule. So a point 3, 2 is not going to look too hot in polar coordinates. It's going to have some decimal numbers on the angle, and it's just going to be bad. And the point 3 pi over 4 is not going to look great when you convert it to xy. So they only look beautiful in their own realm. As soon as you convert it, it becomes ugly. Which is the reason why I say these two systems complement each other. We need both of them. And I just explained how the variable integral, which ends up being the trig sub, becomes a joke of an integral, 1/2 3 squared d theta from 0 to 2 pi, right, to compute the same thing in polar coordinates. So again, what's beautiful in polar is going to be disgusting in rectangular, and what's nice and neat in rectangular is going to be disgusting in polar. And it's just the way it is, because they complement each other. They work with a different base, right? One works as a like as rectangle based, and the other one is circle based. So obviously they're going to have two different geometries. Now, say you need to graph negative 2 pi over 6. Well, that can be done also easily, because negative 2 is right here, and then you go pi over 6. Guys, positive angles go counterclockwise. Like clocks go backwards, right? This is older than clocks. So positive angles go, so you go from the x-axis and your pi over 6 is here. That's your pi over 6. So the point is right there. So that's the point. So if your point is positive point, like I had 3 and pi over 4, you will start on the positive x-axis with radius is 3, and you will swing that positive angle pi over 4. If you have negative radius r, you will go to the negative x-axis, and you will swing positive angle counterclockwise. If you have a negative angle, go negative, clockwise. Let's do one more. So let's say you have 4 negative pi over 6, whatever. So 4 is going to be here on x-axis, right? So we do we graph the radius first, and then pi over 6 negative is right there. So this angle here is negative pi over 6 angle. It's negative 30 degrees. Negative angles go clockwise. So this is our point 4, negative pi over 6. Bueno? So now, conversion in polar coordinates. We are going to build up on polar coordinates. Polar coordinates, as you can see, are two-dimensional, r and theta, right? So what we are going to do is we are going to build on top of those to create a 3D environment. We are going to bump them up into cylindrical coordinates by adding z, or we are going to add another angle phi and create spherical coordinates. So, in order for us to do that, well, we first have to learn how to do the conversion between rectangular and polar, so that we can actually upgrade the polar later into the 3D. It's easy to upgrade 2D, right? 2D upgrade, which was xy, into a 3D. It's just adding z at the end. So, yeah, easy, right? Done. We have a 2D r theta for polar coordinates. Well, first off, I need to make sure that these guys are compatible, because this is eventually going to split into 3D, which will be r theta z, and another 3D r phi theta. I think they switched this in this book to rho phi theta, whatever. So now I want to convert.
Wait, isn't phi like a circle?
You have this one and you have this one.
Oh.
Whatever. Lowercase and uppercase. I see you know your Greek. That's good. Okay, so to convert. The way we convert is we draw this one triangle that has x, y, r, and theta. And you just write 4 formulas that you can write. It's a 3 trig formulas in the Pythagorean theorem. And those are your conversions. What do you have? You have sine theta to be opposite over hypotenuse, so that's y over r. From there, you get that y is equal to r sine theta. You can write cosine theta, which is x over r. Well, that's x equals r cosine theta. Now this creates a set which changes polar to rectangular. It creates a set that changes polar into rectangular because, observe, you need both r and theta to compute x and a y one at a time. So we use a little bit common sense there, right? What else can we write? Well, we can write the tangent theta, which is x over y. It's y over x. So from there you see that you can calculate that theta is inverse tangent of y over x. And you can also write the Pythagorean theorem. Now this set is rectangular to polar because you need both x and a y to compute r and theta one at a time. So these are your conversion factors between the two universes. Now these two universes complement each other. They complete each other. They don't compete. And now, the earlier example that I had of x squared plus y squared equals to 9, well, now it's clear. You can convert this in few different ways. The way I did it earlier is I claimed that this is r squared, and then square root both sides, and I knew I need to put plus minus 3, but I am ignoring minus because r is radius and lengths are never negative. Always when you think about that, how far are you from your house? In miles? 30 miles. 30. And when you're home, how far is this school? 30. It's not negative 30, right? So distance doesn't care about negative sign. It's always positive. A radius is a distance, right? So when we get plus minus 3, when you square root both sides, we just drop the negative. There are no closer schools?
Calc3 for summer too.
Oh, okay. Now, the other way you can deal with this is you can plug in your formulas here, right? This would be, if you plug in these formulas, let's do that in different colors. So how about blue? I will get r squared cosine squared theta plus r squared sine squared theta equals 9. So you can convert it that way as well. You factor out r squared, and you're left with sine squared plus cosine squared. What is that? That's 1. So here's your r squared equals 9, r equals to 3 again. So whether you're going to immediately from here see that r squared is x squared plus y squared and plug that for this, or you're going to replace individual x and a y and then massage the algebra, up to you. Conversion needs to be done because we are going to switch between these systems. When you eventually see the integral from 0 to 1 and 0 to square root of 9 minus x squared dy dx, you are not going to compute this thing over here so that eventually you can do integration by trig sub. Why? You will immediately switch this into a polar based double integral, which we are going to learn in 13.3. I am not teaching this now. But the conversion that we are learning here is important because it's coming up in chapter 13. So please make sure you know this. The last part, in the last 3 minutes of the class, is a representative pizza slice. All right? I mentioned earlier that we can calculate the area of the circle by using the integral of the polar form. That integral formula was studied in Kalk3, and its area is equal to 1/2 integral alpha to beta, these are angles, of function of theta squared d theta. Now, those of you that worry about things that you should worry, which are dimensions, please note that this is two-dimensional formula because it's calculating area. Area is 2D. You have both of your dimensions here. This does not bring a dimension. You see, when you write dx, that's a distance between a and a b, delta x. So dx, dy, dz, those are dimensions. And the multiplication there is actually giving a dimension. But d theta is not giving you a dimension because theta is the angle and it does not have a unit of length. And if it doesn't have a unit of length, it doesn't have a spartal dimension given to it. So both of your dimensions are in f squared. One times, right, one dimensional times the other dimension. And this has no dimension to it. So yes, this is a 2D. Now, if you are still interested in what the hell is going on over here, what is the arc length formula? Does anyone know what's S equal to? Arc length? R theta. So what's theta equal to? Yeah, S divided by R. So if S is in meters and radius is in meters and they cancel, what is the unit for theta? It's unitless. Now we do put radians, right? So we have something, but it doesn't carry dimension because the dimensions of meters and meters, which are actual dimensions for length, are both canceled. This is your physics 101. So no dimension on d theta, both dimensions are within f squared. So now, if I have a circle with a radius 3, we can calculate its area by 1/2 integral 0 to 2 pi because I want the entire circle of r equals f of theta, right? We know that, hopefully. So 3 squared d theta. And when you compute this, you get 9 theta, 1/2 9 theta from 0 to 2 pi, which is 9 pi. If you have a radius 3 and you use the formula, right, remember the tutoring? R squared pi, you get your 9 pi if radius is 3. Right? So this is the way. Now, what this formula can do easily? Well, if you need to calculate 1/8 of the circle or whatever, you can cut with 1/8, right? But see, over here you can play with these. We can play with limits. And you can calculate anything. So, when you're looking at the large pie, and you have 8 slices, and you want to know what is the area of this slice over here, well, you can run the integral for that. This is like the first thing you should run at the next party on a napkin. Just leave it right next to the empty pizza box. We have integral from pi to 5 pi over 4. 1/2. What's the radius on pizza? In inches?
Roughly.
Yeah.
8 inches, 16-inch diameter pie.
So 8, thank you. Yeah. Oh, by the way, they deliver to classroom, if you didn't know. So there you go, right? And you can calculate. This is 5 pi over 4. Because this is your pi, and this is your 5 pi over 4. So you can calculate any amount, upper half, lower half, left upper corner, whatever, right? You can cut in any amount. Now, sure, yeah, you can do that, 9 pi, right, and so on, and you should use it, obviously, clearly. But then we're going to have more interesting shapes, like flowers and, what do you call it? Laminates, and then analysts and all of these kind of things. So we'll deal with all of those things in chapter 13. Okay, so what's for tomorrow? Tomorrow is our chapter 11. We are going to cover first 3 lectures at least, maybe even further. 11.1, 11.2, 11.3. Those of you that want to score the class prep points, right, because that's assigned in the syllabus and it has a percentage to it, those of you who joined late. So the class prep is supposed to be, class prep is described in the syllabus as well over here, and it goes on. So those are the 3 points, right? It is 1-page written summary of the lectures that I will, right? So it's three pieces of paper at most. Do not cut and paste from the book. You're allowed to use any book you want as long as you match the title, and please make sure you put your name and then class prep 11.1. The homework for tomorrow for everyone is just practice the hell out of chapter 10 from